All right, class, this is another episode of chapter 12.2 CFU on transforming to achieve linearity. So we need to look at concept 1, transforming with powers and roots. It is really important you check for understanding that by the time you finish this, you should be able to use transformations involving powers and roots to find a power model, right? That describes the relationship between two quantitative variables and use the model to make predictions. So look at the following example, okay? So the following data represents the lengths and diameters of the humerus bones of this special type of monkeys once thought to inhabit northern Minnesota. So your diameter should be in your list 1. That's your explanatory variable. Your length should be your list 2, and that's your response variable, as you can see from the calculator. So previous studies suggest that the diameter and the length are related by a power model of the form length equals to A times the diameter, but you bring it to a power of 0.7. So they already tell you that that's a power model, right? The length is related to the diameter based on that equation. So transform the original data and use the least square regression to find the appropriate model for the transformed data. So they want you to find the line of best fit, the least square regression line. So, right, so you need to put into a calculator. Now, I want to show you that, how do we find the data for the equation, the actual power model. So we need to go to list 3. Now we need to highlight list 3 first, press enter. Now we need to tell the calculator, okay, so I'm using all of my list 1. So I'm taking list 1 and I'm raising it to 0.7. Why 0.7? Because that's, according to the power model, that's what it has. We don't need to take care of the A right now, right? The A times the diameter raised to the power 0.7. We just need to do the diameter 0.7 for now. So if I press enter, and you see all the values are populated. All right, so we have, we use list 1 for the diameter, list 2 for the length, and list 3 is the diameter but raised to the 0.7 because that's based on the power model, right, equation that they gave us. So I've written down all the values. Now you can do that one at a time, but why should you when you can actually let the calculator do it for you? So for right now, I'm going to show you the scatter plot, the new scatter plot to see what the transform data looks like, but I'll do that in a sec. So right now we need to plot diameter raised to the 0.7, right, which we just found the list, versus the length. The length is your response variable, and diameter raised to the 0.7, that's your new explanatory variable. Now, I need to tell you that in order to find the least square regression line for this new transform data, we need to go to Stat, Calc, and choose number 8, which we have done before. So the X list is L3, that's the diameter raised to the 0.7, and the Y list is L2. And we found that it's the y-intercept is 16.571, and the slope is 19.471. And so in order to put that together in a least square regression line, so the predicted length, which is the length hat in the inverted V, equals to 16.571 plus 19.471 times diameter raised to the 0.7. Okay, I'm going to pause now and I'm going to show you how to find the line of best fit as well as the scatter plot. Okay, so to do the scatter plot, what we do is we go to second, stat plot, and we need to turn the first plot 1 on. And we need to choose the type, which is the very first one. And now my X list has now been transformed to L3. So I need to click second, 3, L3. And my Y list is still, L2. So zoom, 9. So you see it's a fairly straightforward linear model, okay? Now to find the least square regression line, we go to Stat, Calc, and we go to number 8. We just press 8. You see here, XList should be your L3. And then your Y-list should be L2. We calculate. Therefore, we have the line of best fit. All right, let's continue the second part. So you discover a portion of the bone with a diameter of 47 mm. So use your least square regression line or your linear model to predict how long the entire bone was. So we need the least square regression line, which is as follow. So we need to substitute a diameter of 47. And when we do that, you just plug it in. And the final answer will be 304.879 mm. Easy. Okay, so this is chapter 12.2, concept 2, transforming with logarithms. So you should check for understanding that you should be able to use transformations involving logarithms to find a power model or an exponential model that describes the relationship between the two quantitative variables and use the model to make prediction. So basically trying to determine if it's exponential or power model and then use the least square regression line to make a prediction. So, and you should be able to determine which of the several transformation does a better job of producing a linear relationship. So looking at this example, the following data describe the number of police officers per thousands and the violent crime rate per 100,000 population in a sample of states. Use this data to determine a model for predicting violent crimes based on the number of police officers employed. So there are a few things here. One, you don't know if it's a power model or exponential model, but you should be able to tell that the police officers are your explanatory variable and your violent crime rate is your response variable. So you look at the data given. You need to put police into list 1, which I've done looking at the calculator, and we put crime into list 2. All right, class, please pay attention. So because this part is going to be a little bit tricky. So now you can do it by hand by plotting the log of police and the log of crime. And then you can take individual value and you just put it in the calculator, take logarithm of it. So I provided all the values here. Now, did I get all the values individually? No, I actually got it from the calculator. And I'll show you after I presented this how to do it on the calculator. So now I know that my police is in list 1 and my crime is in list 2. Now where do I put log police? I can put it in list 3, and then log crime, I can put it in list 4. So, and then we need to plot. Now, all you need is to plot 3 graphs to see which graphs display a more linear model. So we first plot police versus crime, which is L1 versus L2, right? And that displays a slightly curved pattern. I will show that to you later on. Then we plot police versus log of crime, right? L1 versus L4. And it displays a slightly curved pattern as well. Now, if this would have showed a linear model, then we would know that this is actually going to be a exponential model. Okay, then we need to plot a third scatter plot, which is log of police and log of crime. So which is L3 versus L4. And this shows the most linear of the 3 plots. Now, and in doing so, we can now claim, since it's the most linear of log police versus log crime, then there is a power model, right? Power model may be the best choice to describe the relationship. All right, so I want to show you the scatter plot for L1 versus L2. So second, stat plot. I want to turn the first plot on, and first type, yes, the one on the type, and then L1. versus L2. And I'm going to take zoom 9 to look at the scatter plot. So you can see that it is, fairly curved, right? Fairly curved. If you remove, there might be some outliers maybe, but it's fairly curved. So we now will go back to we know that it's not a good model, not a good linear model. Now we go to the edit, look at our data list. So go to L3, and this L3 will be my log police. So I'm going to put log, and then I'm going to put L1 inside the list to populate log police. And I get all those values. Now I need to go to L4, same thing. Highlight the L4 first before you set the equation. And I put log of L2. And this is log of crime. So then, right, after I've got this for list, I want to now plot police versus log crime. Police versus log crime. Right, police versus log crime, which is second step plot. Turn the plot on. I will now choose L1 versus L4. So my y-list needs to be L4 because it's log crime. And then let's look at the zoom 9. Let's look. It is still curved, right? Still fairly curved. Now we look at the third plot, right? Second step plot. All right, turn it on, everything is on. I'm going to do L3, which is log police versus log crime. And then look at zoom 9. It is fairly linear. All right, let's continue with the last part. Use your model to predict the violent crime rate for a state with 25,400 police officers. So we need to go to stat, calc, number 8, linear regression, A plus BX, and then X list, L3, and Y list is L4. L3 is log police, L4 is log crime. So Y equals to A plus BX. Your A is 2.122, Y-intercept, B is 0.537, and that's the slope. So the linear regression line, the least square regression line, is written as the predicted log crime equals to 2.122 plus 0.537 times log of police. So the question says, what's the crime rate with a state that has 25,400 police officers? So we changed the 25,400 police officers to 25.4. And then we substitute 25.4 into the linear equation. And we get the predicted log crime value is 2.876. Now, what is the inverse operation of log? So the inverse operation of log is actually base 10. So you take 10 raised to the power of log crime equals to 10 raised to the power of 2.876. And that will give you, so the 10 and the log cancels off, and that gives you predicted crime equals to 752.62. So I just want to show you, right, how to work to find the least square regression line. So we go to stat, calc, number 8, and we need to put in L3 versus L4. There we have it.